Welcome to CodersArts. The topic that we are going to discuss today is logistic regression. We will discuss what logistic regression is, where it is used, how it is different from linear regression, and then we will determine the cost function for logistic regression. So the logistic regression is a supervised machine learning algorithm that is used for classification tasks where the goal is to predict the probability that an instance is belonging to a given class. So basically what logistic regression tells us, it tells us the class to which an instance belongs to. For example, there are two classes A and B and there is an instance I. The logistic regression model tells us that the probability of the instance I belonging to a class A is 0.6. That is, there is a 60% chance that the instance I belongs to class A. So the probability of I belonging to the class B will be 0.4, and that is the 40% chance that the instance I belongs to class B. So now since the 60% is greater than 40%, we will conclude that the instance I belongs to class A. So now there are two types of logistic regression. The first is binary classification and the second is multi-class classification. In binary classification, the classes are only two. That means the instance can either belong to a class A or class B. But in multi-class classification, there can be more than two classes. So in this video, we are going to talk about binary classification. The binary classification is used to determine yes-no values. For example, if we want to determine whether an email is a spam or not. So if it is a spam, then the value is yes, and if it is not, the value is no. So now since the machine learning algorithms works on number, it cannot determine the values like yes or no, right? So we use mapping for these kind of values. For example, we map the yes to 1 and no to 0. If the logistic regression tells us that the value is 1, we will consider it as a yes, and if the logistic regression tells us a number 0, then we will classify it as no. For understanding logistic regression, we are going to use a data set that determines whether a tumor is malignant or not. The malignant tumors are considered to be cancerous tumors, so we are going to determine whether the tumor is malignant or not. If it is a malignant tumor, the value is 1, and if it is not a malignant tumor, the value is mapped to 0. Now, before applying logistic regression, we will see that if this problem is solved using linear regression, what are the problems that arises by applying linear regression to it. So if we apply linear regression to this problem, we draw a straight line that passes through the set of data points, and the equation of that line will be y is equals to wx plus b. So now, since the linear regression gives us the continuous values and not the discrete values, how we are going to classify the values to 1 and 0? One way is to do this by determining a threshold value that is between these points. That is, if we consider this point, this value will be 0.5 and this is the threshold value. How we are going to use this value is, you can understand this by that if the predicted value y, if y hat is the predicted value, that is the value predicted by the linear regression by this line, this is the y hat. If this value is greater than 0.5, is greater than equal to 0.5, then we will convert it to 1. And if this value y hat is less than 0.5, we will map it to 0. So by determining this threshold value, that is 0.5, you can see that the values above this are considered as 0 and the values this side of the line are considered as 1. That is, the tumors that are after this line are considered to be malignant. That is yes. By seeing this, we can determine that the linear regression is not so bad for the classification problems. But the problem is when there is a data point that is located here. Let me extend the x-axis. Now, what will happen is the best fit line for linear regression will be this line. And the threshold is 0.5. And if we're going to draw a line on the x-axis, you will see that the values, these points are now misclassified because they all are considered as 0 and above this line they are all considered as 1. So only this point is correctly classified and all these 3 points are misclassified. So that is the problem with linear regression, that if there is an outlier located in the dataset, then the best fit line will change. Using logistic regression, how you can fit these datasets is by drawing a graph like this. This is an S-shaped curve and the threshold value is 0.5. Compared to the linear regression model, this model works very greatly better. And how? Because if you look at this, all the values that are to the right side of this line are considered as yes, and to the left they are all 0. Now even if the data set, a data point like here comes, and if we extend the x-axis, the graph will still classify it correctly. The graph will look like this. So this is a much better model than the linear regression because it still classifies this point correctly and all these data points correctly. The equation of the curve that I just previously explained is this equation. So what it do is it takes the input of the linear regression. It takes the input of z is equals to wx plus b, that it takes the input of the output of linear regression and it converts that value into the values ranging between 0 and 1, since the range of the sigmoid function is from 0 and 1. The graph of the sigmoid function is this, and if you see that this is a S-shaped curve, and if we're going to determine this 0.5 value, this is how we determine it. This is the intersection on the y-axis, so we will put z is equals to 0 since this is z and this is g of z. So by putting z is equals to 0 in this equation, gz is equals to 1 upon 1 plus exponential 0, that is 1 upon 1 plus 1, and this will be 1 upon 2 and this will be 0.5. So the point of intersection is 0.5 and this z takes the output of linear regression and converts it into the values ranging between 0 and 1. Here is the interpretation of logistic regression output. Now this fx is nothing but y hat, and in the linear regression the y hat was wx plus b, right? But in logistic regression the output is this. This wx plus b is nothing but z. Z takes the input of the linear regression and put it in the sigmoid function. So this y hat determines the probability that class is 1. Right? For example, if x is the tumor size and y is 0. If y is 0, then the tumor is non-malignant, and if the y is 1, then it is malignant. So this y hat determines that the probability of that the chance that y is 1 is 0.7. That means there is a 70% chance that the tumor is malignant. And we know that the sum of probabilities is equal to 1. So if there is a 70% chance that the tumor is malignant, there will be a 30% chance that the tumor is non-malignant, and this was 0.7. So this will be 0.3, and 0.7 plus 0.3 is equals to 1. Since there is a 70% chance that the y is 1, this is y hat. So we will classify that the y hat is malignant. So y hat will be 1. This is the equation for logistic regression output that determines the probability of y being 1 considering the features x with parameters w and v. This is y hat. So now the cost function for logistic regression. The cost function for logistic regression is different from the cost function that we use for linear regression. But if we use the same cost function that we use in linear regression in logistic regression, that would be problematic, and we will see why. This is the graph for the cost function that we use in linear regression, and this is the graph of mean squared error. Mean squared error, this is the cost function that we use for linear regression. In linear regression, what we do is we iterate through different parameters to reach the minimum value of the cost function. In different iterations, we do this and we reach the minimum value of the cost function. But if we use the same mean squared error function in logistic regression, the graph would be looking like this. And this is a problematic thing because we see here that there are two minimum at this point. So it will be difficult for the cost function to converge, and since there cannot be two local minimas and there can be only one global minimum so that the cost function can reach its minimum value. So that's why we use a different cost function for logistic regression, and we will see what cost function we use. Now this cost function is used for logistic regression, and this is known as logistic loss. This is the equation, and this L denotes the error that refers to the one data point in the dataset, and the summation of all the errors of the data points in a dataset defines the cost function for the dataset. Now this cost function tells us that if the actual value of y is 1, then the equation for calculating the error is minus log y, and if the true label of y is equals to 0, then the equation used for calculating the error is minus log 1 minus y. This y is the true label or the actual value, and this y hat is the predicted value that is predicted by our logistic regression model, and the error can be computed by using this equation. Now, why we use minus log y and minus log 1 minus y as the equation for calculating the error will be explained through this graph. If the value of true label y is 1, then we use minus log y for calculating the error, right? So we will see that the graph for minus log y is this line. And if we zoom out this area, that will be this graph, you will see that if the y hat predicted by the model is somewhere to be around 0.1. That will be around here. You will see that the value of minus log I will be very much. And by this way, the logistic loss will be very high. So the model will know that it has misclassified. Instead of, if the y predicted will be somewhere around 0.9, this value, then you will see that the value of logistic loss will be very low, right? So the logistic loss and the cost function will know that the dataset has been correctly classified. And if the value of actual label is 0, then the equation that was used for calculating the error was minus log 1 minus 5. And this is because, look at the graph. If the y hat is predicted out to be 0.1 around here, then the logistic loss will be very low, right? And if the y predicted is somewhere to be around 0.7, that is somewhere to be around here, then the value of the logistic loss will be very high, and the logistic regression model will learn that the dataset has been misclassified. So now this is the overall equation of the cost function. And if you see that if the value of y is 1, then the L will be equal to, put y in this equation, then minus log y hat, and this term minus 1 minus 1 will be 0. So 0 multiplied by anything will be 0. So this whole term will be cancelled, and this will be minus log y. So this is the equation that is used when the actual label y is equals to 1. Instead, when the actual label y is 0, then put y is equals to 0 in this equation, and the L will be minus y. 0 into log y, this term will be cancelled, minus 1 minus 0. 1 minus 0 is 1, so minus 1, and log 1 minus y hat. So this was the equation that was used when y is equals to 0, and this was the equation that is used when y is equals to 1. So that's for the today's video. Thank you.